Hello there. I'm redoing section 1.1. We'll see if it goes a little bit better this time. Last time I didn't get any audio, so you couldn't hear me because there was nothing to hear. We'll see how it goes this time. Okay, so we're interested in section 1.1. There we go. And let's see. The first thing I should do is check. Yes. My graphics tableau is working, so we're on the go. Power one ready, Gridley? Yes, I'm in charge, so I guess my name is Gridley. So here are the four things we're going to hit, not too slowly, because you should know all this anyway. But there are a few things that I want to mention so that you're aware of them, and maybe you need a little bit of a refresher on a couple of these things anyway. So here we go. So Renee Descartes is one of the people responsible for what we call the XY plane or the Cartesian plane. Renee Descartes, famous Frenchman, famous mathematician, famous philosopher, blah, blah, blah. He did a lot of things, just like Galileo and most of the others. So here's a plane. You can see the x-axis on the bottom here, the y-axis vertically, right angle between them. We've got four quadrants starting in the upper left, upper right, quadrant 1. Then it goes counterclockwise, 1, 2, 3, 4. Bingo. And back to 1 in case you are doing some kind of repeating situation. Next, all of those points can be represented by order pairs. The x-axis is the horizontal one, the y-axis the vertical one, as you're familiar with. The point of intersection is called the origin, and it divides the plane into the four quadrants that I mentioned a moment ago. Here we go. Now, I would have done this a little bit differently, frankly. I would rather this arrow for the x be down here at the bottom, because if I've got an ordered pair, the way I'm going to find the point is start at the origin and go the x distance, then the y distance to end up with that point. I might as well start the pen going, so I'm going to slip down here. There we go. There's the pen. We'll turn it on, the automatic red, and let's see if we're working here. Go back. It's not doing it yet. Let's see. Maybe it didn't take the pen part. So there we go. Pen. Come on, pen. Give me a red pen. Check it out. Now it looks okay. We're on our way. Next. So what happens if you've got two variables and you've got a bunch of data? Well, one of the things you can do is you can look at what's called a scatter plot. Take all those points, graph them on the same coordinate system, see if you see some kind of a pattern. The ideal one is if you see a linear pattern. That means a straight line. Here's an example of some data. We've got t, that's like the x, 2005, 2006, t for time, obviously, I hope obviously, and E represents the numbers in millions of people. E for employees, that's what it is. Okay, I was wondering. Now, there are two things about this that I wanted to mention. First of all, let's get up here with the graphic stuff. Okay. So first x value, let me try that again. First x value is 2005. That's a pretty big number. You know that if you do that on your graphing calculator, 2005, 2006, 2007 are going to be way too far away from the origin for you to see easily. So one possibility is instead of making y, or x, excuse me, instead of letting x or t being 2005, you let t, got a problem here. You might just let t be a 5, where t equals the years after 2000. That way, instead of having numbers like 2005, 2006, and so on up to 2013, we can instead have numbers like 1, 2, 3, 4, 5, or in this case, 5, 6, 7, 8, up to 13. We'll be able to see it much better on our graph, especially if you're using a graphing calculator. Also, what they've already done on the bottom, this graphing tablet is acting funny, but we'll get through this. If you look above, it says E employees is in millions of people. Already what they haven't done is put 112 million in that block. Well, that's going to make the blocks really big, and that's going to annoy you. 114 million, and so on. So instead, they just say E is going to be in millions, making the numbers much more reasonable for you to graph. So this is what you could do, and I would suggest that you try doing this on the calculator. If you've got a graphing calculator similar to one of the ones that I've got, and I've got a TI-84 CE, no, TI-84 Plus CE or something like that. So what I do is I go into the lists under Edit, and I put in the X values under X1, the Y values under Y, and then I tell the calculator I want a graph of that. When you do, because these are individual points, you want to tell the calculator that you want a scatter plot, one that will look like that, or like this. And you hit graph, and you get a picture that looks like that. Except that what you will have is on the left-hand side, you'll have 104, 106, 108, and so on. And on the bottom, across the x-axis, you'll have 5, 7, 9, 11, 13, and so on, or something similar to that anyway. You could also do it in Excel, too. In Excel, it might look even better. That's your choice. Excel can be handy at times, so if you're familiar with Excel, you might want to give that a shot. Next, the first pair of values is represented by 2005, 112. Remember, it's the year 2005, 112 million. The break in the t-axis, also known as the x-axis, means that the numbers between 0 and 2005 have been omitted. One small note, that's a good way of lying with statistics, by the way. And these are statistics we're using. But we want to be able to see some kind of a pattern. If we miss that pattern, we miss the whole idea of what we're doing. The e-axis, or the y-axis, represents the numbers 0 and 1004 are dropped out. We've got all the rest in there. So t equals 1 could have been used to represent the year 2005. That's all up to you. There's a lot of latitude here, and if you're creative, you can come up with some neat things. If you're doing it in Excel, you don't need to do that. But on a graphing calculator, for example, having 5 through 13 or 1 through whatever can make it easier to do the graphing on your calculator. One way you can do that is to represent it by a bar graph. Now, if you're familiar with the term histogram, you might think, oh, this is a histogram. Well, not really. Notice that the bars, the vertical bars, don't touch each other. If they don't touch each other, those of you who have taken statistics might know if they don't touch each other, it's called a bar graph. If they're touching each other, then it's a histogram. So if you haven't taken statistics, you've got an edge up on the first chapter most likely. The distance formula. Now I'm going to mention something very important here. Let's see, where's my, okay. So we're talking distance formula here. And this graphics tablet or something is slowing down things. I think I'm going to stick mostly with just talking on this one. So follow along, and you can pause at any time you like, of course, while you're taking notes. So the distance formula and the midpoint formula could be confused if you're not careful. And I'm going to give you a couple of tips on making sure that you don't make one calculating, let's see, let me start again. If you're not careful on one, you might do something similar to the way it's done in the other one and totally mess things up. So first of all, to use the distance formula, you need the Pythagorean Theorem. Most likely all of you have taken geometry and you're familiar with the Pythagorean Theorem. A squared plus b squared equals c squared. A and b represent the lengths of the legs. Those are the parts of the triangle that make up the right angle. A and b. Put those together with their angle and you've got a 90-degree angle. Good. The third one, C. C is the longest side. It's called the hypotenuse. If you go by those descriptions, A and B are the legs. C is the hypotenuse. A squared plus b squared equals c squared is the Pythagorean theorem. Make sure you get the legs first, square each of those, add them together, and that'll be equal to the square of the hypotenuse. So let's get closer to the distance formula. We're talking about the distance between 2 points. First thing to note, to make sure you don't make a mistake, is the first point is represented by x sub 1, y sub 1. The ones do not represent the values of the x and the y. The ones represent which ordered pair it is. Because there are ones here, this means we've got the x and y coordinates for the first point. First point as in 1. On the second one, x sub 2, y sub 2. The 2's only mean which ordered pair it is. It's the second ordered pair or the second point. Now, with those coordinates in mind, we want to find out how far it is from the first point to the second point if you're taking the shortest distance, in other words, a line segment. First of all, you would start at this point. You're going to the second point. First thing you're going to do is you're going to measure how far it is in the x direction, how far it is from left to right. To do that, you subtract the 2 coordinates. Now that's very important. It seems really trivial, but you're going to subtract them. And you're going to subtract them taking the second one, subtract the first one. Now that's true of a lot of different things. If you're calculating a discount in a business application, for example, the x sub 1 would represent the original value, the x sub 2 would represent the new value, the new one minus the original one. And that'll tell you how far it's gone up or it's gone down according to the sign on it. Now, all we need is the distance. We don't care about whether it's to the right or to the left. That's why we have the absolute values. So if you get a negative, you take the opposite of it. The distance is always a positive or a non-negative number. You'll do the same thing with the y values. You're going from y sub 1 down to y sub 2. You'll be taking y sub 2 minus y sub 1. We don't care about the sign of that, so we take the absolute value of whatever we get, and that's the distance vertically that we're going when we go from the first point down to the second point. Might be better if I use this. There. I'm going to switch from the graphics tablet to my mouse. It's a little bit awkward, but it works better right now. So we've got the two lengths. We've got the horizontal distance that we're traveling from here to here, and the vertical distance we're traveling from here to here. Next, we've got those two lengths, and the Pythagorean Theorem says, if you look back here, the x sub 2 minus x sub 1 represents one of the legs. The y sub 2 minus y sub 1 represents the other leg. So when we get to the distance formula, this part is going to represent the horizontal distance, the horizontal leg. This will be the vertical leg. We square each one of those. Square this, and we end up with the square of what we need. Well, we don't want the square, we want the real distance. So, take the square root of both sides, that way we get just d, not d squared. We don't care about d squared really, except that it gives us d. Second, it really wasn't necessary for us in this distance formula to actually take the absolute value because we're squaring it anyway. We're not going to end up with something negative if we square it. So the squaring is going to take care of any negative values we might have here. So this is the distance formula. Take particular note. This is the distance from one point to the other. Inside the square root, remember the square root, you're going to subtract the x values. How far is it horizontally from one point to the other? You're going to square it. You're going to do the same thing with the y values. Subtract those, square it. When you get the two squares, then you'll add them together, and last of all, you're going to take the square root of the sum of the squares. And that is the distance formula. One thing that I'm concerned that you could get mixed up with is, remember, you're subtracting here. I'll get back to that in a moment. So here's the distance formula. You might want to put that on the back of a 3x5 card or a 4x6 card if you want several different formulas there eventually. Make sure you take special note of that, carry it around with you, and compare it with what's coming up. So that's the distance formula. Now, this question says, use the distance formula to show that the points 2, 1, 4, 0, 5, 7, those are 3 points. See if they're vertices of a right triangle, because who knows? Those points could look like this, and you really don't know whether this is a right triangle or not. Big question right now. So how do you find out? Well, first of all, you're going to use the distance formula that I just highlighted and find the distance from the first point to the second point. Then you'll take the second point and the third point and find the distance for the second one. Distance 1, distance 2, and third, this is a triangle. You take those 2 points and find what the distance is between those two. That gives you 3 sides. Now remember, in the Pythagorean Theorem, slip back here a moment. On this picture, the 2 legs are the shorter or the shortest of the 3 points, 3 sides. C is the long one. So if we go back here, once you find those 3 distances, the first thing you want to do is determine which one is the long one. That's going to be the hypotenuse. The long side, I'm not going to write that in, equals the hypotenuse. And that, if you use that picture we had earlier, that's going to be your C. The other 2 are going to be A and B. So you're going to take the values that you got up here, and you're going to take the first distance for the first leg, square it. You'll take the second distance, you'll square it. You'll add them together and see if it's equal to that long one squared. This part right here is the part that's in question. Do those equal? If they're equal, then what you've got is a right triangle. If they're off, no right triangle. Now, since we're using calculators, and calculators have a tendency to give you approximations or close values, because, for example, 1/3, just to take something real simple, if you put 1/3 in your calculator, you're not going to get an exact value. You're going to get 0.3, 3, 3. You're going to see several 3s. You might see 8 of them or 10 of them, whatever it is. But at some point, the calculator says, okay, Charlie, you've seen enough. You know what's going on. That's it. But when you go back here and check to see if those 3 are equal, it might be just a hair off. If it's that close, that means they probably do represent a right triangle. If they're not real close, then no right triangle. Now, slip back here just a second. There's the distance formula. Remember, there are minuses inside, at the very inside of those. Keep that in mind with what's coming up. That's 2 points, the distance between them, square root of 45. Now, if you do this with the calculator, obviously you're going to come up with about 6 point something. Check the second 2 points, and it doesn't matter what order you do them. It's the longest is going to be the hypotenuse, and that's what's important. Take those 2 points, and there's the length of that side. Notice already that the square root of 45 is obviously bigger than the square root of 5. So you know that the square root of 5 is not the hypotenuse. It's obviously one of the legs, if it's a right triangle. Third point, subtract, square, add, take the square root. There you go. And even just using the square root sign, you can tell which one's the longest. The third one, if this is a right triangle, this one is going to be the hypotenuse. So you can set up your equation. D1 squared, one leg squared, plus the second leg squared. When you square them, you get the 45 and the 5. Add those together, you get a 50. Now, drum roll. Is the third one a 50? Well, yes, that's sort of obvious. Now, the midpoint formula, and I want you to be very careful that you don't try to find the midpoint and accidentally use that minus sign. That is something that's going to be a problem unless you've memorized this or somehow kept these separate from each other. Here's the midpoint formula. Now, two things especially to notice. First of all, you're looking for a midpoint. That means what you're going to end up with from the two original points is some point. That means ordered pair. How do you get the ordered pair? You have to do two things. First, the x-coordinate of the ordered pair. Add the x-coordinates, divide by 2. How about the y-coordinate of the midpoint? Add the two y-coordinates, divide by 2. Do not subtract. Do not subtract. You add for the midpoint. And likewise, if you go back and you're doing something with a distance formula, make sure you're doing that subtraction and not addition. Don't get those two confused with each other. Very important. It's simple, but it's easy to make the mistake. So here's an example we've got to play around with the distance formula, the midpoint formula, in this case the midpoint formula. So what you've got here are annual revenues of $27 billion. Add a few dollars to that and you talk about real money, right? And along with that, you're talking about the year 2011. Ordered pair. $28.1 billion, 2013. What you've got is an ordered pair. So for the first one of the ways you could write it is you could write it, oops, let me start again. You could use 2011 for the first one, or maybe you just want to use 11. You could even say that the time 0 or year 0 was 2010, and this would be a 1, and that would be a 13 or 3. So there's one ordered pair, 27.0, and you've got a second ordered pair, 13 for the 2013, and 28.1 for the second one. The one thing this has done is it's taken your information that's inside a paragraph and put them into something real simple. One thing that I dislike about doing with word problems is to have to go back and read this paragraph over and over and over to get the numbers. So I separate them out, put them in some kind of order. So what we've got here is we want to find out, without using any other information, what would be the revenue, do you think, for 2012? We have for 2011, we have for 2013. Someone forgot to send us the information about 2012. What do? Well, first of all, we're going to assume that in going from 2011 to 2013, that the revenue is increasing in a linear fashion. If we can assume that, then if we graph these, time versus revenue, we're going to see a line. We're going to make that assumption. Now, if we make that assumption, then I can find out what the midpoint is between those two. Notice 2011, 2013, halfway between is 2012. That's convenient in this case. All we have to do is find the midpoint. What's the midpoint? Let's call it M. Remember, the midpoint, you're going to be adding, dividing by 2. In other words, finding the average. So for the x-coordinate, you'll have 11 plus 13 divided by 2. For the y-coordinate, you'll have 27.0 plus 28.1 divided by 2. I'll say it one more time. Add, divide by 2. Finding the average. So what do you get? The midpoint, which represents 2012. I know you can do this better than I can. So when we take 11 plus 13, divide by 2, we get 12, and that corresponds to our 2012. Good. On the second part, 27 and 28.1 gives us 55.1 divided by 2. We could let our calculator do this job. 27.55. I'm not using my calculator, so I hope this is right. We'll see in a second. If I made a mistake, this is how we do it anyway. Now this would tell us that in 2012, we probably had a revenue of about $27.55 billion for McDonald's Corporation. So let's take a look here. This is one way of doing it. There are other ways of doing it. And this is a simple one because 2012 does happen to be right in the middle. So there we add them together, divide by 2. Not subtraction, that's the distance formula. Add them, divide by 2. That gives us our 2012. They stuck with using the full year. Don't have to, that's up to you. And this is in billions of dollars. So the estimate is, and I actually did get it right on the fly, for the year 2012, we can estimate that the revenue was probably between around $27.55 billion. The actual revenues were probably a little bit above it or a little bit below it. Excuse me. We've got a good estimate anyway. Sometimes all we need is an estimate. Last of all, translating points in the plane. So what are we talking about? Okay, something like this. We've got some kind of figure on the plane. Let's suppose it's a parallelogram like this. Now, translating, what does that mean? That means we've got this figure. Now imagine being able to grab onto that parallelogram and drag it to somewhere else on the plane. But it doesn't bend, it stays the same shape, but you're going to drag it maybe to the right, to the left, some combination of the two, That's what translating means. You're going to keep the look and you're going to move it to a different section of the plane, the Cartesian coordinate plane. So, why do we want to do that? Because computer graphics sometimes depend on that. If you've seen some computer graphics, they include things like transformations. One of those is a translation. That's one we were talking about. You can also have reflections where you flip it left to right, or you can twist it around like as if you're using your wrist, or you can take and use both hands and stretch it wider or higher. So here is our parallelogram. We've got the vertices shown. What we want to do is move that 4 units to the right and 2 units down. All you need to do is do this to each of those ordered pairs. So you take the 3, 6, 4 units to the right means you'll add 4 to the 3, and you'll take 2 and subtract that from the 6. Then you'll go over here maybe to 3, 2. You'll add 4 to the x value, subtract 2 from the y value, then you move on to the next one. Add 4 to the x, subtract 2 from the y, and so on with the fourth one. What do you end up with? There are your simple calculations in this case. There are new vertices after we've translated it or moved it around on the plane without twisting it. And there is our new parallelogram after we've moved it. Notice the shape is exactly the same, we just put it somewhere else. And that is the end of the story. If you have any questions,